Okay, welcome back. We're moving on now to the concept of hypothesis testing, which is really one of the most important things in all of statistical analysis and the use of statistics in research. So it's pretty important that we really understand what's going on here, and it will combine a lot of the concepts that we've been learning about, especially the concepts of the normal distribution or t-distribution, sampling, making inferences about population parameters from samples, etc. So let's jump in. Okay, what we've done is estimate population parameters, and we're focusing on estimating means. There's a lot of other things, and if you look in the book, you'll notice we haven't covered, but there's the similar procedures in terms of estimating variance or difference between means or parameters or whatever, but we'll focus on means for now, just to keep things kind of simple. So we can estimate the mean for a population based on taking a sample, and the sample is going to be a pretty good estimator of the population if we have a large enough sample size, if it's a random sample. We've done a lot of practice with that. Okay, and then last time we talked about confidence intervals. The idea is that 95 samples out of 100 are going to capture the true population mean if we have a 95% confidence interval. Okay, so now what we want to do is test an idea about some cause and effect relationship by comparing two population parameters, so two means. So for example, we'll have an experiment with a control group and an experimental group, and we'll say the average measurement, if it's a medicine or something, the average blood pressure for the control group is X, the average blood pressure for the experimental group is Y, and now we want to see if there's a difference between Y and X to see if our experiment, whether it's a drug or a therapy, whatever, has an effect or not. So we're asking, are the means different? And not only are they different, but is that difference statistically significant? And what we mean by that is that, well, let's think about the things that could cause the difference. The thing that of interest would be a difference caused by causal forces, for instance, the effect of the drug or a treatment. Or it could just be, remember, because we're always getting our population parameter estimate by sampling, it could just be that randomness of sampling that makes it look like there's a difference in those means. So remember, with the 95% confidence interval, 95% of the time our confidence interval captures a true mean. That means 5% of the time it doesn't. So 5% of the time we might be getting a mean that's way to the left or to the right in our distribution of all possible means. Okay, and if we revisit our t-distribution here, or even our normal distribution, we've got this idea that within a bound of roughly plus or minus 2 sigma, we capture about 95% of all possible values for that variable. But that means out here, we're occasionally going to get 5% of the time something that's extremely small or extremely large, where 5% of the time we're going to get those outliers. So the true population means in here, we get a, quote, bad sample, and we get something out here, and it looks like it's different, but it's really not. It's just in this distribution. Okay, so that's what we're asking here. That's what hypothesis testing is going to do for us. It's going to tell us, is this a real difference or just luck of the draw because of sampling? And I think it'll be best to get right into an example, and in the lecture part here we'll work all the way through this example, including setting things up in Excel, and then that'll prepare us well to jump right into the homework, which we'll practice with similar kinds of situations. Okay, so I have a fictional fast food restaurant here, Happy Burger, and they want to increase traffic to their stores so they can get more revenue and make more money. That's what it's all about, right? So they're doing a marketing promotion that offers free dessert with any meal purchase.
Well, at McDonald's, you can buy a Krusty Burger with cheese, right? But they don't call it a Krusty Burger with cheese.
Get out. Well, what do they call it?
A Quarter Pounder with cheese.
Quarter Pounder with cheese? Well, I can picture the cheese, but, do they have crusty, partially gelatinated, non-dairy gum-based beverages?
Mm-hmm. They call them shakes.
Shakes. I don't know what you're getting.
Now, to test whether this gets more people in the stores and gets more revenue and sales, they're going to run the promotion only in a few select areas and then sample potential customers to see if they indeed come to the store more often, and then compare that to a baseline population, which would be where they don't run this promotion. Okay, so I say here, executives want to know if the promotion is working. Does it induce people to eat at Happy Burger more often? Does this drive more customer visits and hence more purchases and hence more revenue? So they commissioned a survey of potential customers in the selected promotion areas and non-promotion areas. We're saying what's the average number of visits to Happy Burger per month for each person surveyed. And of course this, you'll note, is less than 1 because some people don't go at all. So we're averaging a lot of zeros, and then some people go once, and a few people go once, and there's a small number of people that go, 3 or 4 times. Okay, so we're averaging up all of these visits. We want to see if there's a difference between the regions where we did the promo and where we didn't. Now, just looking at the means, we see that this is larger than this, so we might say, hey, the promotion's working. But what we're getting at with the hypothesis test is how can we be sure, because those are both samples. We surveyed maybe 100, 200 people and see how many times they come to the restaurant. Well, what if we just got a bad sample, just out of pure luck, where we sampled more strongly these frequent customers, and that would pull the average up regardless of the effect of the promotion. So we have to do a hypothesis test to help us figure out whether this is a real result or just a chance result. And that's what we mean by statistical significance. Is the result strong enough to where we can say with some level of probability that there's a real effect going on, or is it just pure chance, pure luck of the draw? Okay, and that's what we're saying here. Is this difference in mean visits caused by the promotion, or is it just because by chance we get a non-representative sample? Remember, in sampling, the sample-based estimate isn't always accurate. 95% confidence interval means 5% of the time our sample does not capture the true population mean. So we've got to test whether this difference is statistically significant. And that's what hypothesis testing is all about. Let's break hypothesis testing down kind of into the hypothesis part, and then we'll talk about the testing part. It's very structured. We always follow the same procedure, and we develop 2 hypotheses. One is called the null. It's always indicated as H0, H sub 0. Think about that as the baseline or the status quo, what's normal. And we're trying to disprove this through our experiment. If the experiment is successful, we'll say we reject the null hypothesis and accept the alternative hypothesis. Okay? And this is typically labeled HA, although sometimes it'll be labeled H1. Sometimes this will be H0, and this will be H1. Okay, they mean the same thing. And this is the result we're looking for through the experiment or through the research proposal or what have you. The research hypothesis is sometimes what it's called. So we're going to work with null versus alternative hypotheses. Then we're going to think about working with one-tail tests or two-tail tests. In a one-tail test, we consider only results in one tail of the distribution. Okay, so we've got something like, we've got this distribution, and we'll say, let's say the mean visits is 0.56, and we observe 0.68. We know that's somewhere out here to the right. We're basically going to say how far is it to the right, and what's the chance of getting 0.68 just through sampling. And if that chance is pretty small, we're going to say, okay, it's pretty likely that the promotion is having an effect. If the chance of getting 0.68 just through sampling is large, we'll say, we can't be too sure that the promotion's having an effect. This is a one-tail test because we're moving in one direction.
And we danced all night to the best song ever. We knew every line, now I can't remember. I think I went, I think I went,
And we're basically saying, is this value greater than this value? We might also work with two-tail tests, where we consider results in both tails. We basically are saying, is the experiment mean greater or less than the null hypothesis mean? Or in other words, we might be saying here, is the experimental mean just equal to or not equal to the null hypothesis mean? And as we work through problems, it'll be pretty obvious once we get a handle on this, whether we're working with one-tailed or two-tailed tests. My example problem about Happy Burger and their promotion, that's a one-tailed test. In a minute here, we're going to get into actually doing hypothesis test. We'll set it up and we'll work it in Excel, but we need to talk about a few more things first. Errors in hypothesis testing. Okay. In research, error is a tricky thing. We need to be really careful about it because there's 2 ways to be wrong. Okay. It's not just you're right or you're wrong. There's multiple ways to be wrong, and we refer to these as type 1 and type 2 error. Okay, so in type 1 error, what we're doing is incorrectly rejecting a null hypothesis that is true. And kind of put it in plain language, what we've got is a false confirmation from our experiment. You'll often hear in medical testing, this is the idea of a false positive. Okay, the idea if we're testing a person for a disease, the null hypothesis is that you don't have the disease. We run the test and it shows that, oh, you do have the disease, but that's wrong. The null hypothesis is actually true, and we falsely rejected it by saying the person does have the disease. Well, what's driving that? That's because the test screwed up. There's an inaccuracy. There's some kind of error rate in the test. Okay. So the idea here of false confirmation or falsely rejecting the null hypothesis, that's type 1. And then type 2 error would be where we incorrectly accept a null hypothesis that is false. Okay. And you think about this as this is in medical testing. This would be a false negative. So we say we run the test. We say, you don't have the disease, but you actually do. And here is just where the test wasn't strong enough to capture the truth that you do have the disease. So we want to reject the null hypothesis. Remember, the null hypothesis would be that you don't have the disease, and that's false. But we can't reject it because our test is too weak. Okay, so you can think about this in terms of a weak or inconclusive experiment. And we might suspect that the null hypothesis is false, but we don't have enough evidence, or we don't have this indicator to reject it. And kind of thinking about a balance between type 1 and type 2 errors is really central to really all research, and especially kind of trial-based or experimental research. You've always got to kind of think about whether your research design biases you in favor of one or the other, because the only way to reduce the incidence of one error is to increase the incidence of the other. Now, the book has this really nice table that helps us think this. We've got the truth. Okay, what is the actual situation? Of course, we don't know this, but we're testing for it. And then the decision we make based on our test results. Okay, so we reject the null hypothesis, but it's true. We have committed type 1 error. We have a false confirmation of our proposed experimental effect. So this would be in Happy Burger. This would be where null hypothesis is that the promotion doesn't have an effect. There's no difference in the mean number of visits from people in the promotion areas versus the non-promotion areas. And we go ahead and run an experiment and say, but there is an increase, at least in our samples indicate that there's a higher level of visits in the promotion areas. Even if that's not true, okay, and this is kind of that luck of the draw, we just by chance got an extremely large sample mean. Now, of course, if the hypothesis is true, if the promotion has an effect, and we reject the null hypothesis that the promotion doesn't have an effect, there's no error, so that's okay. So it's okay to be out here. Now, let's consider the other option where we don't reject the null hypothesis. We say we don't have enough evidence to reject the null hypothesis. If the null hypothesis is true, of course, that's okay too. We don't have an error there. So there's two ways to be right, just like there's two ways to be wrong. However, if we don't reject the null hypothesis, so the null hypothesis, remember, is that there's no effect from the promotion, and there actually is an effect from the promotion. The alternative hypothesis is true, but we don't have enough information to make that conclusion, then we're making a type 2 error. So what we're saying here is the idea of a false negative, or we have insufficient evidence to confirm the effect of our experiment, in this case the promotion. Okay, let me give you a classic example here from the field of jurisprudence, the law. Type 1 error in a courtroom situation where someone's on trial for a crime. The type 1 error would be convicting an innocent man, okay, of a crime he did not commit. And your type 2 error, okay, kind of the opposite error, would be letting a guilty man go free. If you have any familiarity with our basic legal institutions, you'll note that we have this concept from our common law heritage, English common law, of the presumption of innocence.
In the criminal justice system, all defendants are innocent until proven guilty, either by confession, plea bargain, or trial by jury.
You can kind of think about that with the idea of presumption of innocence. Do we favor type 1 errors or type 2 errors? Well, the presumption of innocence is the null hypothesis, and the burden of proof is on the prosecutor to prove guilt, the alternative hypothesis. So we have a built-in bias towards avoiding type 1. We do not want to convict an innocent man, so we have the presumption of innocence and a high burden of proof. You know, in a jury trial for capital offenses, you have the proof burden of something like beyond a shadow of a doubt or beyond a reasonable doubt. And even if we strongly suspect somebody of committing a crime, we don't have evidence beyond a shadow of a doubt. If there's some lingering little doubt, we, according to our legal norms, we cannot convict that person. So we might be letting guilty people go free and committing type 2 errors. Okay, so we're going to be more okay with type 2 errors because we want to avoid type 1 errors. At least in our legal system, that's kind of how things are structured. And that is because we have institutions that try to protect the individual against an abusive government or abusive, actually even just other citizens who might want to use the law against people. So we have this high standard of proof, so we'll maybe be more willing to let guilty men go free than convict an innocent man, at least according to our principles and theory. Now, in an individual situation, sometimes you get overzealous prosecutors who would rather do the opposite because they want results and being tough on crime and that kind of thing. But the idea that we favor type 2 errors has been encapsulated for a long time in our legal tradition. And you have the great English jurist William Blackstone, who wrote the famous commentaries on the laws of England in the 1760s. And if you have ever studied the law, you'll be familiar with Blackstone as one of the great minds in the law. He said, "It is better that 10 guilty persons escape than that one innocent suffer." So that's kind of the legal maxim that encapsulates this idea that in the courtroom, you want to minimize type 1 errors, even if that means accepting a higher incidence of type 2 errors. We can think about that in exactly the same kind of matrix that we had earlier. Okay, so let's say we've got a person on trial for a capital crime. Let's call him Todd. And and we kind of set up the null and alternative hypotheses. The null hypothesis is that Todd is innocent. That's the presumption of innocence. And we're going to say, do we have enough evidence to reject that or not? Alternative hypothesis, HA, is that Todd is guilty. We'll only go with that if we can strongly reject the null hypothesis. So if the null hypothesis is true, Todd is indeed innocent, and we find him guilty, we've committed type 1 error. Remember, the presumption of innocence concept and the burden of proof on the prosecution and the standard of proof beyond a shadow of doubt helps us to kind of minimize this. Of course, if Todd's guilty and we find him guilty, that justice has been served there. And of course, we find him not guilty, and if he truly is innocent, then we also have good justice happening there. But if we find Todd not guilty and he actually is guilty, now we've committed type 2 error. And we're more willing, remember, to accept this because we want to avoid this. So there's an inherent trade-off. If we want to minimize type 1, we're going to have to accept more type 2, and vice versa. If we want to minimize type 2, we have to accept more type 1. Okay, and as I've said, we won't say a whole lot more about type 1 and type 2 error here. We'll just do hypothesis tests and talk about the strength of the results in terms of p-values. But this is something that you really have to bear in mind whenever you're doing research and whenever you're testing differences such as we're about to do. Now, by the way, it just occurred to me that one of the greatest trials of all time, a type 1 error was committed, but this was for our benefit.
Jesus, the endless praise to thee, whose boundless mercy hath for me and all thy hands have made, an everlasting ransom paid.
Okay, so there's a few more definitions and things we need to cover here, and then we'll be able to move on and do some examples and then the homework. Significance levels. How strong must the evidence in favor of the alternative hypothesis be in order for us to reject the null hypothesis? Or we could also think about this in terms of probability. What probability of type 1 error are we willing to accept? That's denoted by what we call the significance level alpha. And we could really set this wherever we want. We could say 20%, 10%, 5%. The most common ones used in science and research are 0.01 or 1%, 0.05, 0.1. Okay, and actually the most common of those is 5%. So we've got a 5%, you kind of think about it this way, 5% chance, type 1 error, false positive, or convicting the innocent man, rejecting the null hypothesis when it's actually true, so making a mistake, type 1 error. That kind of flip side of that is we've got a 95% confidence level, and it's a little similar to the concept of confidence interval. We could say we're kind of 95% confident that the results we generated here, this difference that we observe in two means, is not just by chance or by randomness, but it's actually a causal effect. We can say we're 95% sure of that. Okay. And related to the significance level is the idea of a rejection region. Okay, with the rejection region is that we observe sample data that will lead us to reject the null hypothesis. Smaller alphas give us smaller probabilities of type 1 error, and therefore stronger evidence needed to reject a null hypothesis. This would correspond to a higher burden of proof in a courtroom setting. Larger alphas then, of course, mean there's a larger probability of type 1 error, and will reject a null hypothesis with weaker evidence. Okay, now another way to think about this, and actually the more common way to think about it, and I think maybe the more intuitive way, is in terms of probabilities, or p-values. What is the probability that a random sample is at least as extreme as the observed example? If you remember the concept that a sampling distribution is normal or t-distributed, and t is kind of closely related to normal, okay, we know the probabilities beyond a certain cutoff level by reference to a z or t table, or using Excel to calculate that for us. So again, we've got this idea of the bell-shaped normal or t-distribution, okay, and we're saying this is our null hypothesis mean, we'll call it mu 0, and our sample comes out up here, we'll call that mu alpha, and we're saying that how far out would we be in a normal or t-distribution to where we would expect to observe that? Well, if it's just a normal distribution, if we're 1 sigma out, we have, let me just start over on that because I had to run these calculations. We're not using the empirical rules because we're thinking one-tailed now, but we've got mu 0, and then in a normal distribution at 1 sigma, we've got about 84% of the observations to the left of 1 sigma, and then at 2 sigma, we've got about 98%, approximately 98% of the observations less than that. So we're basically saying relative to our null hypothesis mean, and we'll convert our sample mean into sigma intervals, distance from the null hypothesis one. Now we'll use t-distributions now because we're dealing with the effect of smaller sample sizes, and remember the concept that the S is not a perfect estimator of sigma, so we'll use t-distribution instead of z-distribution. But anyway, we'll say how many t-distributions is our sample mean away from our hypothesized mean, and if it's more than 2 sigma, so if our t-value winds up to be like something like 2.1, we'll be able to say this: 98% of the time, from sampling, the sample mean would have been in here. So we'll be able to say there's only a 2% chance that we would have got this extreme of a value just by sampling. Or so the alternative way of thinking about that is a 98% chance that there's some kind of causal relationship that's causing our hypothesized mean, we'll call it the mu alpha, to be larger than the null mean. Okay? So in other words, the smaller that p-value, the less chance that there's not a causal relationship happening, or there's not some kind of an experimental effect happening. We look for small p-values, we have greater and greater confidence in the results that we're finding. Okay, so now let's apply this concept to Happy Burger and my little story I've been telling. And there's my data again, based on the surveys we did for the promotion areas. Remember, people get a free dessert with every meal. We're going to see if that draws more customers. That has 0.68 average visits per month of the people we surveyed. And the non-promotion areas have only 0.56 visits per month. That looks like there's an effect there, but we have to test it and see how strong that effect is, how likely we would have gotten that difference just through randomness and sampling. Okay, so to set up our hypothesis test, we have to have a null hypothesis and an alternative hypothesis. Null hypothesis, H0, is that there's no difference in mean visits. And we can quantify that. We will here in a minute, but I want to kind of think through the logic first of what we're doing. We're basically saying the difference between the non-promotion areas and the promotion areas is 0. An alternative hypothesis would be something like this. Well, we could just say that the promotion leads to the difference we observe, which is 0.12 more mean visits. Or generally speaking, then we could say the promo mean is greater than the non-promo mean. And what the p-value method does, it says what is the probability of getting this sample mean just through randomness and luck of sampling, even if the true mean for promotion areas is not different. In other words, assuming the promotion has no effect, what's the chance that we would observe this from a sample, this result from a sample, just getting unlucky, just getting a bad sample? Well, I shouldn't say bad, an unlucky sample. Okay, so that's the question we're asking. We've got our null and alternative hypothesis. We're familiar with the different kinds of error we have to be aware of. Now I think we're really ready to do some math and to answer that question and come up with a p-value. So let's do a hypothesis test. So I'm going to be a little bit more specific now about how I set up the null and alternative hypothesis. I'm going to go ahead and say our null mean, and I could technically label this mu sub 0. Okay, mu 0 goes with h0. Is 0.56. And that would indicate there's no difference between the promo and non-promo. Our alternative mean is greater than 0.56. Now you might think, well, the alternative mean could be 0.561, and that's not a practically significant effect. So we might go ahead and put a threshold in like this. Threshold, like, we want to see if the promo leads to a 10% increase in visits. And what would a 10% increase be? Well, that 10% times 0.56 equals 0.056, and adding that on to see if there's that big of an increase, we'd get something like 0.62. Okay, I'm rounding a little bit. So we might say, let's say the hypothesis mean mu alpha. I should really put an alpha on this one. I'll put an alpha on this one. Mu alpha is greater than 0.62, greater than or equal to, let's say. That would indicate that there is indeed 10% increase in average visits due to the promotion. That's our experimental effect, if you will. Okay, and when we set this up in Excel, we'll do both ways. We'll just test what's the p-value of the mean being just bigger at all, and then we'll say what's the p-value of the mean being this much bigger. So we'll do h0 equals mu 0 equals 0.56, and we'll do ha mu alpha equals, or mu a, I should be mu a, not alpha. Mu alpha equals greater than 0.62. We'll actually test those both here in just a minute when we get into Excel. So what we need to do is come up with a t-value in terms of standardized units in the distribution. How much farther to the right that is in the distribution, and what's the probability that we would get that versus this just through sampling. We calculate that test, what we call the test statistic. We're finding a t-value. If this was normal distributions, we'd be finding a z-value. Remember the formula for t-value. We did this in the last chapter. X bar, that's the sample mean, minus the hypothesized baseline mean. So it's x bar minus mu, divided by our sample standard error. That's the standard error of the sample statistic. Okay, and that's the sample standard deviation divided by the square root of the sample size. So you'll notice, well, we need a sample standard deviation and sample size. I've gone ahead and added those in here. So let's say my survey sample size was 123 people surveyed, and let's say my standard deviation was 0.45. Gets us 1 sigma or 1 standard error there. Right, so now we could actually calculate that t-value based on all this sample data. Okay, the x bar is 0.68. The null hypothesis is 0.56. So we'll set that up, and then the survey sample standard deviation is 0.45, and it's divided by the square root of the sample size of 123. Okay, now I could get out a calculator or pencil and paper and write that all down and come up with a t-value. But why be tedious when Excel can do all that for us? So let me show you how to do that very quickly and easily within Excel. Okay, so notice here I've just copied in my data. There's my hypothesized mean. That's my baseline mean, 0.56. Here's my sample mean, 0.68. My sample standard deviation, 0.45. My sample size is 123. Okay, and that means my degrees of freedom is 122. Okay, now I'm calculating my t-value. Now pay careful attention to my formula here. Okay, I'm taking D2, which is my sample measured mean, minus D1, which is my hypothesized baseline mean. So there's the difference in means. That's on the top half of that division sign, divided by D3, which is my sample standard deviation here, over the square root of D4. So if I set that up, that's calculating the t statistic for me. And we get a t of 2.95. Just think about that based on what you know about a normal or t distribution. Sigma minus sigma in a normal distribution, remember I just said that 84% were less than 1 sigma, and what did I say? 98% roughly of the observations were less than 2 sigma. Now, For t distributions with small degrees of freedom, the percent under the curve is going to be much lower because the t distribution will look more like this. But for t distributions with larger degrees of freedom, remember our threshold value is about 30. So this is a pretty large degrees of freedom. So we've got a t distribution that pretty closely approximates the normal distribution. So if we're bigger than 2 sigma, we've got 98% of the observations to the left of this. Well, look, we're not even bigger than 2 sigma. We're almost to 3 sigma. And what would be left? What percent of observations would be left of 3 sigma? I can find that pretty easily. Norm dot dist sigma of 3, mean 0 and 1. That's the defined parameters of a normal distribution. 99.86%. So if we're close to 3 sigma, and again, I'm thinking about a normal distribution here, but remember, t distributions with larger degrees of freedom are getting closer and closer to the normal distribution. And I'm now capturing to the left of this 99, what was it? 99.86. 99.9, let's round it. 99.9% of observations would be to the left of that. So we could alternatively say there's a 0.0, I'm sorry, that we could alternatively say there's a 0.1%, 0.1% chance of getting a sample mean out here without having experiment effect. 0.1% chance. Okay, 0.1% chance of getting that result if there's no experiment effect. So are we confident that the experiment has an effect? Yeah, we'll say we're highly confident that the experiment has an effect. And here I've calculated the p-value. The p-value is calculated by the formula t.dist.right of Rx, which is our t statistic, and then our degrees of freedom, which here I just plugged in. We could have done cell reference as well. Okay, so we've got a p-value of 0.001, which means, remember, a 0.1% chance if we convert that to percents. Yeah, it's about 0.2 because this is a t distribution. That's the difference between t and normal. In perfectly normal, I had a 0.1. In t, I've got 0.19. Okay, but those are pretty close, and we'll say that because that probability is so low that we would have gotten that same result just through chance, we're going to be pretty confident that our experiment has an effect, or our promotion has an effect, with a p-value of close to 0, 0.2, and therefore a significance level, which would be 1 minus that. Our significance level here is going to be 99.8%. I'll come back to the relationship between p-values and significance levels here in just a second. First, before I move out of here, I want to remember, all I'm testing here is whether the sample mean is larger than the hypothesized mean. Well, remember, back here I said I want to set a threshold to gauge the level of effectiveness. Maybe to say, is the experiment 10%? Does it generate 10% more visits? That would require a hypothesized mean of 0.62 for the null. So let's go ahead and do that. And that's what I've done over here. Okay, I put my null hypothesis at 0.62, and everything else the same. My x bar is 0.68, my sample standard deviation 0.45, my sample size is 123. I was playing around with different sample sizes earlier. My DOF is 122. Okay. And now we'll run our t-value, same calculation. Okay, it's the difference between the observed sample mean and the hypothesized mean. So it's G2 minus G1 divided by the sample standard deviation over the square root of the sample size. And so that's the math I've done here. Set up my t-value calculation. If you aren't following with me, that's okay. We'll do this again. We'll have to set up this again when we get into the homework problems. So I've got my t-value. I use that t-value to calculate my p-value. And that is, again, the t.dist.right. We're only working with the right tail here because we're just looking for greater than. And that's G7 divided by my degrees of freedom. Let's use a cell reference for my degrees of freedom. Okay, and that comes out to 0.07. Convert that to percent with 2 decimals. Okay, now we don't have as small of a p-value. We've got 7%. In other words, we might say there's a 7% chance that we would observe this difference in these sample means. Or we'll say here there's a 7% chance that we would get this kind of sample mean just through sampling randomness, even if there weren't a difference here, even if the experiment had no effect. So can we say that with a high level of confidence that there's a difference in the experiment and baseline group? Yes, but can we say with as high a level of confidence that it's a 10% increase? No. In fact, we can only say that with a 93% confidence, because 7% of the time we would get that difference just through sampling. That brings us back to this idea of significance levels, alpha levels. What's the relationship? Well, it's this: the sample evidence is statistically significant at the alpha level only if the p-value is less than a. What the heck does that mean? Let me go back to this example. So here, can we say the result is significant at the 5% level? No, the p-value is greater than that. Can we say it's significant at the 10% level? Yes, p-value is less than 10. So this result here, this is not significant at alpha of 5%, is significant at alpha equals 10%. Just on a side note, when you read research reports, they'll put their summary data out there, and they'll show you the t-values or the z-values, normally t-values, and they'll put 1 asterisk, 2 asterisks, or 3 asterisks on it, typically to indicate at what level it's significant. 1 asterisk would be 10% significance, 2 would be 5%, 3 would be 1%. So you want to look, if you've got those 3 asterisks there, you've got a alpha significant at alpha of 1% or a p of less than 1%. And we just answered the question there: how statistically significant is our Happy Burger test? If we're just thinking about the difference, it's highly significant. It's significant at 99.8% level. We might call that the mere difference in means test. And we've got 93% for an alpha equals 7%. So that's significant at the 10% significance level. We could say the 7%, but we generally use those 3 thresholds: 1, 5, and 10%. So this is significant at the 10% level. We put 1 asterisk on the t-value. Right, the t-value equaled 1.4 something, we'd put 1 asterisk on it. Up here, the t-value equaled 2.95. We'd go ahead and put 3 asterisks on it, if we were reporting this in some kind of official research publication. Okay, I think that's grounds us pretty strongly then in this concept of hypothesis testing and how we do it and all the terms. So now we're ready to move on and tackle some homework problems.